Assalamu alaikum. Today we are going to discuss Article 29.5 from Survey and Jude. An article is about applications involving charged particle moving in a magnetic field. As we already know, Lorentz force, which is F equals to Q into V cross B, but in the presence of both electric and magnetic field, the total force will become F is equals to QE plus QV cross B. So this is the modified version of Lorentz force, and in most of the cases, you'll see that this is the case. And when electric force is absent, then you are only considering the magnetic force, but in the presence of electric force, the total force will be the sum of these two forces. Now coming to the applications, the first application is the velocity selector. In many experiments, constant velocity is required of the charged particle, which can be achieved by number one, applying combination of electric and magnetic fields. And when you apply electric and magnetic field simultaneously in a way that, if you can see this diagram over here, the magnetic field is going into the plane of the board, or in this case laptop, and the electric field, it is directed from top to bottom. Now if we have a source and we release charged particle, and we make sure that the magnetic force and the electric force, they balance each other, so that the charged particle moves in a straight line. So in this figure A, the charged particle will experience downward force, and in figure B, after balancing the particle, it will move in a horizontal direction. So after achieving the equilibrium condition between the electric and the magnetic force, we can write Fe equals to Fb, that is QE equals to QVB. Cancelling Q from both sides, we get E equals to VB, and V is equals to E over B. So this is the condition for the velocity selector when we want to move our charged particle in a straight horizontal line. We must balance these two forces. So particle with this velocity will pass undeflected. Neither it will move up nor down towards the plates. It will move straight in a horizontal path and towards the detector. So this is the first application of a magnetic field. Now for mass spectrometer. Mass spectrometer is an instrument which is used to separate ions of different elements, and because some of the elements, they have different isotopes of different elements. So if you want to separate, suppose a hydrogen, deuterium, tritium from one another, mass spectrometer becomes very handy in it, or it separate ions according to their mass to charge ratio. So it is used for both of these purposes. A beam of ion, first, this mass spectrometer, it is connected with a velocity selector, because using this velocity selector will only allow those particles to move in a straight line which are required. So we set the magnetic and the electric field in such a way that only the selected particles are allowed to pass through it. All other will be deflected towards the plates, and there is an opening, and these required particles, they will move into this opening. Here we have a magnetic field, a constant uniform magnetic field, and in the presence of this magnetic field, these charged particles will deviate from their original path and will move in a circular path. So depending upon their mass, they will acquire their desired radius. That is, we have already studied that radius of the charged particle moving in a circle is directly proportional to the mass. So if we have heavier mass, it will have a greater radius, and if we have smaller masses, we will have a smaller radius. So this is all the explanation of the mass spectrometer. So now if we want to find the mass to charge ratio, we have the equation that is m over q equals to rb over v. This is from r equals to mv over QB, which we have already studied in the previous article. From here, uh, because we are interested in knowing the mass to charge ratio, so it will remain here, and we have RB over V on the other side. So from equation, this equation, we can write m over q equals to r b naught b over e. From where we have used this e over b, it is from here, because we have used a velocity selector over in the mass spectrometer. So this velocity is equals to E over B, as we have seen in the velocity selector article. So I can replace this V with E over B, and this is what I get to find charge mass to charge ratio. So this B naught is the magnetic field which is present in the within the chamber of the mass spectrometer, and this B is the magnetic field which we are using in the velocity selector. So this is the difference between these two B's. The application of this is J.J. Thomson tube, which was used to find charge to mass ratio of electrons. The third application is cyclotron. Cyclotrons are basically used to accelerate charged particles like protons to an extremely high speed, that is approximately equals to the speed of light. The cyclotron consists of a chamber. Mostly these chambers are commonly known as D. These chambers are conducting. So these are the conducting chambers. I'll show you the figures in a while, which shows how they look from inside, and all is all which the process which is taking place will be taking place in a vacuum. Okay, now assuming that the magnetic field is coming out of the board, or in our case out of the laptop screen. Now suppose we release it in chamber a 1 mega electron proton. So this is the figure of cyclotron. These are the Ds, that is two chambers. They are placed side by side to one another. They look like this from inside, that is they are sort of hollow, and the magnetic field is going into the screen. No, sorry, it is coming out of the screen, because I have a dot over here. So it is coming out of the screen. So now I have released 1 mega electron volt energy proton in this chamber. At this point, I have released a proton, and this proton in the presence of magnetic field, because we have magnetic field over here, in the presence of magnetic field, it will start moving in a circular path. And the moment it reaches this edge, we have applied a potential of, let us suppose, 20 kilo volts over here. So in the presence of potential on this chamber and this chamber right now, the direction of the electric field is from this D to this D, and as the proton, it moves out of this chamber, it faces this electric field, and while doing so, it gains energy, and it gains about, I think it was 2 kilo electron volts. So I think it gained 2 kilo electron volts of energy. So okay, I have certain numbers over here. We have a proton with 1 mega electron volt energy, and it comes out, the speed is also known, and that speed is 1.4 into 10 raised to the power 7 meters per second. Let us suppose that the magnetic field is constant and is 1 Tesla, and the radius, initial radius of the proton with which it completes its semicircular path in the first D is 15 centimeter. So the proton will move in a circular path, but when it reaches the edge of the D, a potential difference is introduced between the D's. So the edge at which the proton has reached is at higher potential than the other edge of the D towards which it is moving. So after gaining certain energy, I just want to check the value of the energy that it has gained. Okay, so the particle will gain 20 kilo electron volts of energy when it will move through this potential over here. So it will gain 20, let me correct it. It will gain 20 kilo electron volts of energy, and when it reaches over here, obviously it has gained energy, and with that energy it has gained speed as well. So we have already seen that R is equals to mv over qb. So whenever a particle is moving with greater speed, it will have a greater radius. So now it during its motion from this edge to this edge, it has gained 20 kilo electron volts of energy, and because of that it has gained speed as well. So its kinetic energy has increased, and now with a greater speed, it will again, when enter into this chamber over here, it will have a bigger radius, and again it will move in a circular path because we have magnetic field over here, and now it will move in this circular path and reaches this edge over here. Now we have reversed the polarity. The system works in a way that when the particle is over here, it enhances the speed of the particle so that it may gain its energy and speed and reaches the other D. So when it reaches over here, the potential, we reverse the polarity of the potential. Now the direction of the electric field is from this D to this D, and during the charge motion from this edge to this edge, it will again gain 20 kilo electron volts of energy, and obviously more speed with a greater kinetic energy, now it will enter this T, and obviously with a greater path or a greater radius, it will move over here, and the process goes on, and the particle will keep on gaining kinetic energy during its path, and finally we can take out the particle after its spiral motion within the chamber through some exhaust or some area from where we want this particle to leave the chamber, and then can be used to bombard different samples to get our desired results. So this is how we make the particle accelerate in the cyclotrons. So this is the formula through which we know that R is equals to 2mv over qb square, and this is the potential, and this is the mass, and this is q and b square, and on this formula the radius is dependent. So with every semicircle within the chamber, the radius is increased by 1% in the particular case that we have discussed over here. So this is how a cyclotron works, and just a point to remember that the work is done by electric field only, because this electric field is accelerating the particle. The magnetic field cannot accelerate the particle. Magnetic field can only change the direction but can do no work on the particle. So all the work that is being done in a cyclotron is because of the electric field, and the magnetic field is only used to confine the particle. So these are few applications related to article 29.4. Now we will discuss the last article very briefly, that is 29.6 and Hall effect. Hall effect is defined as when a current carrying conductor is placed in a magnetic field. So whenever we have a current carrying conductor and we place that current carrying conductor in a magnetic field, a potential is generated in a direction perpendicular to both the current and the magnetic field. So if you look at this, this is a current carrying conductor and it is placed in a magnetic field. So this is the direction in which the potential is being generated, and this is perpendicular to the direction of current as well as the magnetic field. So this is observed by Hall and is known as Hall effect. The application of Hall effect is that it gives us information about the sign of the charge carriers. It also tells us about the density of the charge carriers and the magnitude of the magnetic field. In the figure, we have seen that current is moving in x direction, magnetic field is in y direction. We have two different types of charge carriers, that is a negative and positive. Mostly Hall effect is effective in solid state physics, where we have n-type and p-type semiconductors, and in n-type semiconductors the majority charge carriers are electrons, and in p-type of semiconductors the majority charge carriers are positive ions or holes. So the Hall effect tells us about these negative and positive charge carriers, and is mostly helpful in semiconductor devices and physics. So for negative charges, the drift velocity is towards left, and for the positive charges it is towards right. The magnetic force will be pointing in the upward direction. So now let us consider a conductor, and we have a magnetic field that is going into the plane. And for this case, we have negative charge carriers. So when we have negative charge carriers and the current is moving in x direction and the field is going into the plane, um, these negative charge carriers will start accumulating at the top of the conductor and leaving behind all the positive charges at the bottom. And this accumulation keeps on going unless and until this electric field and electric force balances this magnetic force. So when the balance or the equilibrium is attained, then no more of the negative charge carriers move towards the top of the conductor. When this balance is achieved, we can say that we have certain Hall voltage, and for this Hall voltage can be noted by using very sensitive voltmeters or potentiometers. In case of positive charge carriers, the drift velocity, only the direction of the drift velocity will change, it will move towards the right. And all the positive charge carriers, they will start accumulating at the top and leaving behind all the negatives at the bottom. The force they will experience, that is the magnetic force, again it will be in the upper direction. And when they achieve balance between this magnetic force and electric force, then no more accumulation takes place, and Hall voltage can be seen. The direction of Hall voltages for both the carriers is in opposite direction to one another. So this is how we can by using this simple technique, we can find the polarity of the charge carriers, that what sort of charge is being used what are the majority charge carriers in a device. So this is how it is important. So for mathematical expression, we have to balance these two equations. After balancing, I can see that drift velocity into magnetic field is equals to electric field. Here this H is for Hall, so this is a Hall field right now. We know that in the figure we have shown that the width of the conductor is d and t is the thickness of the conductor. So when we go back over here, okay, we also know that potential is equals to E into D, electric field into distance or displacement. So VH is equals to VD B into D. From here I have written this VDB. So this is another way of expressing Hall voltage. From our previous knowledge, we know that drift velocity is equals to I over NQA. I can replace this VD with the I over NQA, and also as I have shown you in the figure, the area is length into width, so thickness into width. So I can write this area like this, and for simplification, putting these values and expanding A over here, I simply cancel out this D and I get IB over NQT, where this T is not for time, this is for thickness of the conductor. And from here I'll come across a new constant, that is Hall constant RH, and its value is equals to 1 over NQ. So this is the value of Hall constant. So I can write the equation as del VH equals to RH IB over T. Again, this is not time, this is thickness. So example 29.8, which is related to Hall effect. A rectangular copper strip 1.5 centimeter wide and 0.10 centimeter thick carries a current of 5 ampere. Find the hall voltage for a 1.2 Tesla magnetic field applied in a direction perpendicular to the strip. Data given is I 5 ampere, B 1.2. As we are using copper, so number of free charge carriers in copper is 8.49 into 10 to the power 28 per meter cube. We have done in we have also calculated this value and then have used this value in number of examples done before. Q is 1.6 into 10 to the power minus 9 and the thickness is 0.001 meters. We'll simply use this formula, putting the values. I get 0.44 into 10 to the power minus 6 volts or microvolts. So this is all about chapter number 29. So we are done with that. Next we'll be doing chapter number 30th.